Number 94. Calculate the pH at the following points in a titration of 40 mils, which is 0.040 liters, of a 0.100 molar barbituric acid, a solution. They gave us a Ka value of 9.8 times 10 to the negative fifth, and we're titrating it with 0.100 molar potassium hydroxide, which is KOH. And now we're at letter D. So in this case, we are adding 40 mils of the potassium hydroxide solution. So a couple of things here. Basically a couple of things. We're on part D already. So we've introduced this idea of this like battleground, chart here that happens when we have a titration. And we know that we have a titration because we're dealing with KOH, and KOH is a strong base, right? That's on your list of 6 strong bases. And we're reacting it with this barbituric acid, right? Barbituric acid? I have no idea, right? B acid, right? But that type of acid is not on my list of 6 strong acids, so it's classified as a weak acid. And just for simplicity purposes, we did label this acid as HA. Ha! So that's why I just put, okay, here's my HA, the barbituric acid. That's the buffer acid, A for acid. And then if we're doing this chart, you have to have the conjugate base, so that's just a general A minus. We did find out from before that, we had 0.004 moles here. So if you have any questions as to where we got any of this from, go back to letter B in this number. That's where we go into depth as to how we got this information. So we're just going to pick it up from here. Just know that if you are using this little chart, right, we only can use moles. So only moles allowed. No molarity, no grams. So the first thing is that we have to find out how many moles of the KOH we're adding. We know that we have a molarity, 0.100 molarity, and they give us a volume. Remember the molarity formula. Molarity equals moles divided by liters. We have the molarity. We could solve for the liters. They gave us a milliliters, and then we can get the moles. If I want to just rearrange this, it would be moles equals molarity times liters. Just easier for the video, so I'm just going to use this formula. So the moles of the strong base would equal the molarity of the strong base, 0.100. I'm just going to multiply that by the liters. Now this is milliliters, but I can convert this into liters. It's pretty simple. Mils to liters, all you got to do is just divide by 1,000, right? Or you could just take your decimal, plug it to the left 3 times, and you'll come out with 0.040. Right? 1, 2, 3. Yep. That makes sense. So 0.040. Beautiful. So if I just multiply these two, I'll get the starting amount of moles of the base. So this is the moles of the KOH. And that looks like 0.0040 moles. And that's starting with the KOH. So I have 0.0040, if you want to put it, but it doesn't really matter, moles of the KOH. And they didn't say anything about starting with the buffer base, right, the conjugate base. So I have to assume that I have 0 of this. Now comes the fun part. And what we're going to do is we're going to see if the buffer is going to prevail, or is the strong base going to prevail in the battle between weak acid versus strong base. Now, how are we going to figure that out? The first thing is that you're always going to subtract the number that they gave you for the strong base. So I'm going to subtract this. And I'm using my colors with the purpose, right? The blues are always the base numbers, and the red is the acid. It just makes it easier for understanding what's going on. And just know that this number is going to transfer over to the acid and base side because there's a battle. So 0.004 on this side and 0.004 on this side. Now, we just have to figure out, well, what's going on between these numbers? Am I going to add them or am I going to subtract them? The same thing for this. But if you don't start with any buffer of the base, right, it's blue, and you're adding more base, I literally just gave you the answer. It's kind of hard to explain without giving you keywords. But this would be additive. And remember, there's no such thing as a negative amount of moles. So if you started off with nothing, you can only go up from there. So 0 plus 0.004 is 0.004 moles of the buffer base. And now coming over here, this is a battle. I have amount of acid and I have an amount of base. Remember, these will collide to make water. And then the acidic or the basicity, falls apart. So this would always be subtracting. But if I do subtract these numbers, I get nothing. This completely cancels out. So this cancels out. And this cancels out. There is no more acid. Oh boy. If there's no more acid, do I have a buffer solution? No, I don't. Since I don't have any number here, I have no more buffer. The buffer has been completely killed off. And all you have that's left is this. So I can only work with this. And if you only have just a conjugate base, we go back to the ice table. I know you love it. We say, we always want to have two numbers here because then we can throw it into the Henderson-Hasselbalch equation. But since we only have one number here left, I can't use the Henderson-Hasselbalch because I don't have a buffer anymore. So when you don't have a buffer anymore and you have weak base left over, this is the ice table. Unfortunately, guys, I have to do it to you because that's the only way that it can get done. So, pause the video if you need to. I'm just going to erase this math because I want to kind of have that space to work with the ice table. Thank you. And now we're just going to take it with, this is what we're starting with. We are now starting with this amount, only the base, because now it's got to come back to equilibrium. So A minus, and remember it's a base, so you have to add water. And this comes to equilibrium because this is a weak base, and the base will turn into the acid, and then plus the OH minus, right? And now anything that is charged is always aqueous. And since the HA is a weak acid, that's also going to be aqueous as well. Remember, the water is always going to be a liquid, which never counts for the ice chart. Now let's just do our little ice table here. We'll call it ICE. And now initial, I stands for initial, right? But if you're now using an ice chart, only molarity is allowed to be in here. So that's another thing to remember, guys. We can't just plug in 0.04 into here because this is a mole value and we need a molarity here. So I have to now go back to molarity. But that's pretty easy because molarity equals moles divided by the liters. So we just found out the moles, right? The moles remaining was 0.004. But now the liters are going to change because you're mixing 40 mils with 40 mils. That's a total of 80 mils. When we're talking about liters down here, we're talking about total, the total volume. So you have to combine the 40 and the 40. Literally, it would be the 0.04 plus the 0.04 because now you have a total of 80 mils, aka 0.08 liters. So now let's do that math. So the bottom is 0.08, and then let's just do the division. 0.004 divided by 0.04. Just kidding, 0.08. And I get 0.05 molarity. This is now the number that goes here. 0.05. And remember, water we don't care about when we're doing the ice chart, so get rid of that. And we don't start with any HA, right? There was no more acid, so 0, and no more, we didn't make any hydroxide, so 0. And now we're just going back to a regular ice table, right? C stands for change, the change in the concentration. This has got to increase because you started with nothing. So this would be plus, and this would be minus. We don't know by how much, so we just label it a variable, minus x, and plus x. And then the E stands for equilibrium. So you pull together the I and the C. So it'd be 0.05 minus x, and x, because 0 plus x is just x, right? Now we take our equilibrium value and plug it into our K equation. However, we made OH minus, and we're starting off with a base. What do we need? Do we need a Ka value? No. We need a Kb value. This one is a little messed up. They gave us the Ka value, but we have to get a Kb value because I'm starting with the base and I produce hydroxide. Those are the signs that you need to know or recognize in order to say that, hey, we need a Kb. So let's just do that side little thing here. I pulled up the equation that we should be using, right? Kw equals Ka times Kb. And maybe if I can just kind of move this over again. I guess that's fine for now. But if we're trying to solve for a Kb, all we have to do is just divide by the Ka value. So I'm just going to do that right now. So we're going to take this Ka value, put it on the denominator, and this is now going to equal the Kb. The Ka was what they told us, 9.8 times 10 to the negative fifth. And the Kw, we're assuming that we're at room temperature, so Kw is 1.0 times 10 to the negative 14th. So let's figure that out. Kb equals the Kw, 1.0 times 10 to the negative 14th, divided by the 9.8 times 10 to the negative fifth. And let's find out that Kb value that we're going to use. So 1 times 10 to the negative 14th divided by 9.8 times 10 to the negative fifth. And we get 1.02. That's good enough. Times 10 to the negative 10th. Okay, so pause the video if you need to, but I do need to move some things around. I'm going to get rid of this chart right here because we don't need it anymore. So it's going bye-bye. So just pause the video if you need it. And then what I want to do is I want to get rid of this as well, because I want to kind of get it a little bit not messy. So that's going. And then the last thing that I'm going to do is I'm actually going to just shift the ice table over to this side, just so that I have more room on the top here. So maybe I'll just put this, I'll put this over here. And I'll put this over here. Beautiful. And maybe I'll drop this down a little bit. Sorry, guys. As I'm doing this, I hope your day is going really well. Do anything fun today? I'm doing these videos. It's pretty fun. Anyway. All right. So let's take our equilibrium and plug them into the Kb expression, right? Remember, Kb equals concentration of the two products divided by the one reactant because water doesn't count. So we have the two guys up top here. We got the one thing down here. So it'd be HA times OH minus divided by A minus. The Kb was 1.02 times 10 to the negative 10th equals, we'll do like that. This was X at equilibrium. And now here comes the issue. If we keep this minus X in here, that's going to give us the quadratic equation. We want to do like a little check just to see if we could sneak by doing the quadratic equation. And what we do is we just say that, okay, since this Kb is so small, it's 10 to the negative 10th, that means that at equilibrium, I should mostly have reactants. So if I started with reactants, and I'm going to end with mostly reactants, the drop, this minus X, is probably so small that nobody cares about it, which means that I could basically get rid of this. and get rid of this as well if you want to do that. Then we're going to just check to see if that is, doable, and then we can go on our merry way. So let's just pretend it doesn't exist, and we're going to just solve for x. So I'm going to do my cross multiplying, right? X times x is x squared. And then this equals 1.02 times 10 to the negative 10th times 0.05. I get 5.1 times 10 to the negative 12th. What was that? Cool. I want to get rid of the squared, so I'm going to square root it, but I got to be fair. I got to do it on both sides. So x equals, let's just use maybe a couple of decimals here, 2.26. Let's do 2.258. That sounds better. 2.258 times 10 to the negative 6th. Okay, now let's just do the 5% rule. That's the check to see if we can move forward with this number. And what we do is we take this value and we divide it by the initial. It's always the initial. So I'm going to take that and divide it by the initial and times it by 100. If this answer is less than 5%, we can continue. But if the answer is over 5%, we can't continue and we have to go back and put that negative x in there and do the quadratic formula. So let's just check it out. 2.258 times 10 to the negative 6 divided by 0.05 times 100. Ooh, very It's not even a percent. It's 0.004516%. So I'm just going to give that a check. I'm going to say, okay, we passed the 5% rule, and I'm just going to get rid of this math. And now we know that this x value is all cool. Okay, and remember, the x value, we still want to find the pH, so I'm going to take it from the OH value, right? So my OH amount equals 2.258 times 10 to the negative 6th. Now, how do I go from an OH to a pH? Well, there's a couple of ways to do it. Let's just maybe move this over a little bit, just so I maybe have enough room. And I guess I'll do it up here. Now we remember the formula. Yeah, we could do the formula just like this one, but instead of Ka, it's H plus, and instead of Kb, it's OH minus, right? So I can kind of rearrange this. If I wanted to just start it off, I would say that Kw equals H plus times the OH minus. And if I want to solve for H plus, I just divide on both sides by OH minus. So that's what I'm just going to do here. So Kw divided by OH minus is going to equal H plus, because from there I can finally find a pH. The Kw is the one that we already know, 1.0 times 10 to the negative 14th, and the OH is what we just found out, the 2.258 times 10 to the negative 6th. So let's find out that H plus value. H plus equals 1.0, and I should put brackets around this, right? The concentration of H plus, the concentration of OH minus. There we go. 1.0 times 10 to the negative 14th divided by 2.258 times 10 to the negative 6th. Okay. We're almost there. H plus equals 1 times 10 to the negative 14th divided by 2.258 times 10 to the negative 6th. And I get roughly 4.429. 4.429 times 10 to the negative 9th. And that is now the molarity. We're almost there. We still got to find the pH. But we're getting there, guys, right? Let me just drop this down because we're coming down to it. Now, how do I go from an H plus to a pH? That formula, is pH equals negative log of the H plus concentration, right? Just plug in that number that we found in here. So pH equals the negative log of the 4.429 times 10 to the negative ninth. Oh my goodness. This is nuts. This one was nuts. And it was all because at the end of the day, when you did that fighting, there was no more buffer. Just sometimes it's like you really, really wish that you had those two values there. Or else you're doing it like this. Okay, so negative log of 4.429 times 10 to the negative ninth. And I'm going to say that this is a pH of 8.35. And it kind of makes sense. Remember, we only had base left over. So now we're really high up on that pH scale. Now we turned. I think last number was like 5 something. Now we're completely basic. We're over 7. And kind of makes sense. We only had base at the end of the fighting between the titration. So our pH is now 8.35. I think there's one more left in this question. So hang tight. All right? Hopefully it's not as long as this one. But if you can do this one, you basically can do them all. All right? Okay, I'll see you in a little bit. And if you wouldn't mind, please press the subscribe button. That will help my brother and I out tremendously. We really do appreciate you guys. I'll see you in a little bit. Okay, bye-bye.